Alrighty. So we're gonna resume our talking about the concept of complex power. And the first thing that we're going to talk about today is power factor. So mathematically, power factor is defined as the ratio of the average power absorbed by a load divided by the apparent power absorbed by a load. And this is the same as the cosine of theta v minus theta I, or cosine of our power factor angle theta s. Factor is a measure of the efficiency of power transmission to or from a network.
Here's what I found.
My watch wanted to talk to you guys about power factor as well, apparently. So since this is related to a cosine function, it should be fairly obvious that the values for power factor can range anywhere from -1 to +1. Negative power factors correspond to how well something is supplying, or how efficiently something is supplying power to a system. And positive power factors correspond to how well something is absorbing power from a system, okay? So a power factor of +1 means that a load is absorbing 100% of the apparent power that is delivered to it, meaning that all the apparent power is real power. And a power factor of -1 means that a load is supplying 100% of the apparent power. So it's actually probably a source or something like that in your system. Power factors of 1 and -1 are not considered to be leading or lagging because they're operating at 100% efficiency. A power factor of 0 means that we're at a maximum value of inefficiency. So effectively, that's only true whenever we have a load that is either purely inductive or purely capacitive. None of the power is absorbed. All of it is just being sent back and forth, right? So our average power is 0, our parent power is whatever it is, all right? When the power factor angle theta s is between 0 degrees and 180 degrees, we say that the power factor is lagging. And so this means that the voltage, or excuse me, the current lags the voltage. And when our power factor angle is between -180 degrees and 0 degrees, our power factor is leading, meaning that I leads V. Okay. Technically speaking, loads that operate below a certain power factor threshold, so usually somewhere around 95% or 97.5%, incur fines from an electric utility. Okay. So as a consumer, what we pay for is P average. And as a distributor, what the electric utility creates is the apparent power, the magnitude of S, right? So if the ratio of what we're absorbing and paying for compared to the apparent power is too low, we get fined because we are introducing an inefficient system to the grid, okay? So we can fix this by using a process called power factor correction, which we're going to talk about a little bit later in the class. But effectively, as a home consumer, you're never going to have to really worry about that. Even if you have your dryer and every fan in your home running at the same time, because you're part of, effectively, your street is all connected together in one string. There's no way really that your individual power factor is ever going to dip below probably 98%. Okay. But if you were an industrial consumer like a laundromat or washateria, where your entire business is based on rotating electrical machines and stuff like that, you may have to apply power factor correction techniques to keep yourself from getting fined. And then for heavy industrial consumers, like manufacturing plants and stuff like that, whenever they use conveyor belts, large cooling fans, all that kind of good stuff, that's another place where you're likely going to have to see some sort of power factor correction happening. Okay. All right, so we have introduced, gosh, I think at this point, pretty close to 10 relationships having to do with complex power. So the next thing that I want to do is introduce the concept of a power triangle, which is just a handy graphical device that helps you remember how things are related. So for a generic load, Z is equal to R plus JX. And let's assume the resistance and reactance of this load are positive for now. The complex power absorbed by this load would look something like this. So here we have our real axis. Here we have our imaginary axis. And let's say that this two-dimensional vector, S, represents our complex power, where S is simply RMS phasor voltage V times the complex conjugate of RMS phasor current I. The projection of S onto the real axis is our average power. And the projection of S onto our imaginary axis is our reactive power. So in rectangular coordinates, we can see that S is simply P average plus JQ, right? So the real component of S is the average power. The imaginary component of S is our reactive power Q. And this is symbolized on our triangle, giving us a pretty easy relationship, right? Well, on our graph, we can see that the complex number S makes some angle with the horizontal axis. This angle is theta S, our power factor angle. And the length of this vector is the magnitude of S, or our apparent power. So in polar form, the complex power is expressed as the magnitude with an angle that is our power factor. So our power triangle contains all of the information, right? As our real power, our reactive power, our apparent power, our power factor angle. And we can use just basic trig identities to figure out what any of those individual parts are without having to memorize all of those equations that we came up with at the beginning of the last class. Brandon.
To measure leading and lagging like in real life, they're just the multimeter. Put it on your hot wire. Go.
No. So to measure leading and lagging, you need to either know what kind of load you had to begin with, or you need to look at the instantaneous values for voltage and current. So roughly every year, not any this year, I think because I specifically said I didn't want to see it again. A senior design group does some sort of power factor correction scheme, which involves switching in capacitors and all that kind of stuff to adjust the power factor. And probably the hardest part of that project is figuring out a scheme by which to measure the instantaneous value of the power factor. So if you have an oscilloscope and you can literally look at the voltage signal and the current signal, you can physically see which one is leading or lagging pretty easily. But most people don't want to have to use a $1,200 to $1,500 piece of equipment to determine that. Okay, they want to set up some sort of scheme using a microcontroller to figure out what's going on. And generally speaking, that's done by measuring a couple of different things, right? So if you know the zero crossings for the voltage and the current, so effectively you can say, all right, so every time my voltage signal is zero but increasing, I give myself a timestamp, right? And every time my current is zero and increasing, I give myself a timestamp. If you know what your frequency is, then due to that change in time, you can easily determine what your power factor angle is, and from there determine whether your system is leading or lagging, right? Because our power factor angle is literally right up here. If theta v minus theta I is positive, we know that it's lagging. If theta v minus theta I is negative, we know that it's leading. So if we can measure that angle, that's all we need to do, right? So measuring power factor is really all about measuring that angle. You could also, this would be a more complicated technique, use a couple of watt meters and all that kind of stuff to figure out what portion of the real power is actually being absorbed. And then you can get your ratio there. But it's hard to tell what's leading or lagging from that. The general assumption though, because industrial loads use inductive systems much more so than capacitive systems, the overwhelming majority of the time, you're going to have a lagging power factor. Like the only practical, and I'm using air quotes here because it's not particularly practical thing that I can think of, where you would have a capacitive or a leading load would be you hooked up a capacitor bank that was oversized to do your power factor correction, or a rail gun. That's it. Pretty much everything else that I can think of is going to be an inductive and therefore an inductive load and therefore have a lagging power factor.
So if your utility company tries to charge you extra electricity, get a rail gun, solve the problem.
Sure, that sounds like a very reasonable solution. Yeah. So, all right. So our power factor, or excuse me, our power triangle has in this simple graphical representation our average power, our reactive power, our apparent power, and our power factor angle. We can also tell just by looking at our power triangle whether or not we have an inductive load or a capacitive load, right? So the fact that this theta S lies in the first quadrant means that theta S is positive, and therefore this represents a lagging or a load that is operating at a lagging power factor, right? What if theta S were in the second quadrant? What would that represent? Yeah, so it's exactly right. So it's still lagging, but it's actually supplying power while it lags. If our angle theta S were in quadrant 4, that would be leading while absorbing power. And if our angle theta S lies in quadrant 3, that would be leading while supplying power. Okay. All right, so anybody have any questions regarding the power triangle? Jared,
This isn't about the power triangle, it's actually washing machine.
okay.
So, how do you know that, you go under the 90%?
How do you as a user? You don't. You get a letter from the utility company saying that you did.
But how do you know that? How can they tell that you did?
So that's where it gets into having watt meters and all that kind of good stuff. Like they're able to tell the way that they meter your power is able to determine what you're absorbing versus what they're supplying, right? Which is literally what the ratio of the power factor is. And it's all about averages as well. Like, so if your home ever consistently dipped below or anything like that, like if your power factor was low for the duration of the month or whatever, you'd probably get a letter in the mail saying you're doing something real fishy here. Because it would require continuous operation of all of the inductive loads in your house to drive it that far, which is why I'm saying something like a washateria where there are all of the loads are effectively induction motor related and lots of them are going to be on at any given time is likely going to drive your power factor down. Right? So for instance, if we plugged up that fan, that box fan right there, and we had it on its lowest setting, I would be willing to bet that that fan as an individual load operates somewhere at around 85% at the lowest rotational speed. At the highest rotational speed, it's probably somewhere a little less than 60%. I can say this because of how many of those senior design projects that I've seen where they literally just use a fan from the building and use that as kind of a way to measure things or whatever, right? That fan only represents a small portion of the electrical loads, even in this room, right? So like the utility company doesn't look at it on a load by load basis because that wouldn't make any sense. Like I doubt they could figure out how much each load or the power factor at which each load is operating. But they know what frequency the power they're delivering to you is. They know the RMS voltage, and they know the current. And from that, they can tell for an individual consumer based on their monitoring system what your power factor is at any given minute. And if it stays low for too long, such that on average, your power factor was below the threshold for that billing cycle, you would receive a fine. Does that make sense? So it's not like, oh, it dropped below 97.5% for 14 seconds, you owe us 3 cents. Because the overwhelming majority of the time, it was probably well above that. But if you have a big industrial load where it's consistently below there, that's an issue. The issue really comes from the fact, so do you guys know anything about the concept of ampacity? Probably not, okay. Ampacity is the technical term for how much current a wire can safely carry before it melts its insulation, which then could potentially cause short circuits, fires, and all that kind of good stuff. All wires are rated for their ampacity, and the ampacity values are related to the apparent power, okay? So the wires that are connecting the receptacles here in this room, if that is let's say it's on a 15 amp circuit, So which means it needs a 15 amp breaker to control it or whatever. That 15 amps is 125% of the ampacity of the wire or somewhere close to it. There's an extra 25% safety factor built in, right? What was the other one? So if the load that you are designing your system for is operating at a very inefficient power factor, the current that you're designing for is actually probably a lot larger than you need, which means that they have to use either larger wires, which contain more copper and are therefore more expensive, or the same size wire, but with a better temperature regulated sheath or insulator around it, which is also more expensive. So effectively, they are fining you because they are having to put infrastructure in place to deliver you a certain amount of apparent power, but you're not actually absorbing all of it, right? So it still, that large value of power still had to be generated, which costs money, regardless of whether the load that you're connecting is capable of actually absorbing it. Something related to this that I saw in the news, I want to say maybe the last month or two, there was a large aluminum foundry in Texas that went under. And so while that aluminum foundry was in operation, they had a lot of infrastructure in place to support the operation of that plant. Well, when it went under, effectively, the utility company was able to generate too much power. So then the consumers were able to purchase. So their whole system was operating at a low power factor because this foundry went offline. What that region of Texas did was encouraged a whole bunch of crypto miners to move into that area, literally several hundreds of crypto miners to move into that area to effectively make up the load that used to be that aluminum foundry in order to balance things out. So anyway. Any other questions, power triangle related or adjacent? All right. So I would like to introduce some alternative relationships here for complex power. All right, so since Ohm's law in the RMS phasor domain is simply V times IZ, V is equal to IR in the DC or time domain, phasor V is equal to phasor I times Z in the frequency domain, and then if we put squiggles over our phasor voltage and phasor current, we have our RMS frequency domain relationship. So because Ohm's law is Ohm's law in any different analysis method that I can think of, we can develop relationships for complex power that utilize this relationship. So what I mean by that is we could say that the complex power, which by definition is our RMS phasor voltage I times the complex conjugate of our RMS phasor current I, is equal to IZ times I conjugate, or, so what happens when I multiply the complex number by its complex conjugate? Anybody remember? Angle goes away, but something else happens as well. Let's do this out here as a quick aside. Let's say I have a complex number A that is the magnitude of A angle theta A, and therefore A conjugate is the magnitude of A angle negative theta A, right? If I multiply those two quantities together, I get the magnitude squared, right? So when I multiply RMS phasor current I times its complex conjugate, I get the magnitude of my RMS phasor current squared, which I'm just going to call IRMS times Z. And I can break this down into IRMS squared times the magnitude of Z angle theta Z for a polar form representation, or IRMS squared R plus J IRMS squared X for rectangular form representation. So it literally tells me the losses that I have due to the real part, and then the losses that I have due to the imaginary part. Similarly, I can say that S is equal to V times I conjugate is the same as V times V over Z conjugate. When I conjugate a fraction, this is the same as V conjugate over Z conjugate. So I need to conjugate both the numerator and the denominator. And so what that's going to give me is my RMS voltage squared divided by the conjugate of my impedance. I could spread this out into a polar form representation and a rectangular form representation if I so chose. But it's not nearly as concise and pretty as the current relationship, so I'm not going to do it. If you're going to use these guys, it's probably going to be this one that you're going to utilize. We can use these relationships and come up with simple complex power relationships for resistors, capacitors, and inductors that effectively tell us how they behave. All right. So for a resistor, since the impedance is purely real, it's fairly straightforward that our complex power is simply this guy right here. IRMS squared times R. And if we look at this relationship, what's the complex conjugate of a real number? The real number. So it's just going to be VRMS squared over R. These are nothing more than our DC power relationships from, I don't know, way back in engineering 120. For a purely inductive load, we're going to have J omega L, the impedance of our inductor, times IRMS squared. And for our voltage relationship, this is going to look like J times VRMS squared over omega L. so to be clear, because it might seem like there's supposed to be a negative J here, right? When we have J omega L in our denominator, and then we conjugate that, that's negative J omega L, and 1 over negative J is where this positive J out front comes from. And then finally, for a capacitor, we have negative J divided by negative J multiplied by IRMS squared over omega C, or negative J omega C times VRMS squared. So what do these relationships tell us? Resistors only absorb average power, right? Because there is no imaginary part to either of those relationships. Inductors absorb reactive power only, right? Because we have a positive J based relationship. And capacitors absorb negative reactive power or supply reactive power to systems, right? Which we can see because of the negative sign in front of our J's here. Okay. So this is telling us exactly how all of our regular circuit elements behave, which also leads into the concept of power factor correction of how do we inject or supply VARs to a system. Before we do that, let's work an example problem. So let's say that I have a 120 volt RMS, 120 angle 0 degrees, volt RMS voltage source. Which is used to supply 3 loads like so: ZA, ZB, and ZC. And over here on the right-hand side, let's say that we have current source, 5 angle 45 degrees amps RMS. And let's say that ZA is 10 plus J8 ohms. ZB is 12 minus J3 ohms. And ZC is 8 angle 30 degrees ohms. And we want to know PA, the average power absorbed by load A, or impedance A, magnitude of SB, the apparent power absorbed by impedance B, QC, which is the reactive power absorbed by impedance C, and PFS supplied. So that's the power factor at which each source supplies power. So let's talk about this stuff. All right. If we want to use our simple relationship, complex power is equal to the RMS phasor voltage V times the complex conjugate of the RMS phasor current I, we would have to know literally the phasor voltage drop, or RMS phasor voltage drop, and RMS phasor current flowing through every element. So that would be 10 pieces of information, of which we're given 2. I would argue that that's a bit tedious. Okay. for our loads, ZA, ZB, and ZC, we can use our alternative relationships. We just developed 5 minutes ago with that, which are dependent only on knowing either the RMS phasor voltage or the RMS phasor current, right? So that effectively eliminates half of the information that we're looking for. So do you guys want to work this trying to determine voltages or currents or some combination thereof? Voltages, okay?
You already know two of the voltage. The ZA and CC, over the ZA and CC.
I disagree with that sentiment. The only voltage I know is that there is a 120 angle 0 volt RMS potential difference between the top left corner of the circuit and the bottom of the circuit, which does not correspond to the voltage drop over any of my impedances by themselves.
Or wouldn't the ZC just be corresponding to data?
That is true. So we could say VC having this polarity is 5 angle 45 degrees amps RMS times 8 angle 30 degrees ohms, which is nothing more than, let's see, 5 times 8 is 40, right? And 45 plus 30 is 75 degrees volts RMS. So from this, the complex power SC is going to be 40 volts RMS quantity squared divided by 8 angle negative 30 degrees ohms. 160 over 8 is 20, right? Wait, 40 times 40 is definitely not 160. Yeah, 1600, 200. 200 angle positive 30 degrees amperes. And I don't know what the cosine of 30 degrees is off the top of my head, so I'm going to have to get a calculator now. How do you know? Oh, wait, I actually should know that.
That one's the answer.
Yeah. So using this calculator that I don't care for, let's see. Mode complex, 200 angle 30 converted into rectangular is 173.205 plus J 100 volt amperes. Cheston, you got a question?
Yeah, I was wondering what the, I forgot what the asterisk is.
So the asterisk.
You don't have it drawn on there, but.
Yeah. So the asterisk is the complex conjugate operation, right? So let me scroll up here real quick. It's probably going to lose this stuff. Okay. I'm using this relationship right here to determine the complex power absorbed by element C, right? Which is the RMS voltage quantity squared. So this is the magnitude of the phasor voltage squared divided by the conjugate of the impedance. So for an RMS phasor voltage of 40 angle 75 degrees, the magnitude is just the 40. So that's why I squared that. And the impedance ZC is 8 angle 30 degrees. So the complex conjugate of 8 angle 30 is 8 angle negative 30. Is that legit? All right, so I now have apparent power, average power, reactive power, and my power factor angle. Which of these parts do I need to answer part C of this question?
Power, you, 100 KR.
Exactly right. So I need this guy right here. The imaginary part of the complex power, QC, will be 100 volt amperes reactive. All right. So we got one of our 5 quantities of interest taken care of. Anybody have any suggestions regarding any of the other parts?
You do a modified nodal top node.
Sure.
The voltage for CV and
Right. So if we make the bottom node our ground and the top node our unknown quantity, we should be able to perform Kirchhoff's current law at that top middle node, which would allow us to determine the voltage drop over ZB, positive polarity on top. And then from that, we could do effectively this KVL to find the voltage drop over our impedance ZA as well. Okay, so that sounds reasonable. So let's do that in blue. So I'm effectively calling this node ground, although I don't particularly need to. And I'm going to call this voltage RMS phasor voltage VB. I can see that VB minus 120 angle 0 degrees volts RMS divided by ZA plus VB divided by ZB minus 5 angle 45 degrees amps RMS is equal to 0. So to be very clear here, I'm saying I don't need to know what the voltage is at this node, at least for this particular calculation, because Kirchhoff's current law is simply the sum of the currents flowing out of that node. And this current of 5 angle 45 degrees, we can easily see is the current flowing in, which is where that negative sign came from. So I like how you called it modified nodal, because it does require modifications to our conventional ACL equation. But I hope at this point in our analysis careers, we can all understand why we're able to do that. So because our calculators, to my knowledge, are incapable of solving even this one equation, one unknown system, we have to do a little bit of algebra to make things work here. So that's going to look like VB times 1 over ZA plus 1 over ZB is equal to 120 angle 0 degrees volts RMS over ZA plus 5 angle 45 degrees amps RMS. And therefore, if my thing will scroll, VB is 120 angle 0 degrees volts RMS divided by ZA plus 5 angle 45 degrees amps RMS multiplied by ZA, ZB over ZA plus ZB. Where this term over here on the right-hand side comes from the fact that I'm dividing by 1 over ZA plus 1 over ZB. Same thing as multiplying by those two impedances in parallel. I get 77.917 angle negative 0.238 degrees volts RMS. Somebody, okay, got a thumbs up from Ian, so I'm going to assume either this is correct or we both made the same mistake. Either way, we'll move along from here. So from this, SB is 77.917 volts RMS quantity squared divided by the conjugate of 12 minus J3. What's the conjugate of 12 minus J3, Justin? 12 plus J3. Absolutely right. Thank you. Which I get to be 490.813 angle negative 14.036 degrees volt amperes, or in rectangular form, 476.158 minus J 119.040. So, Luke, which part of all of this junk that I just wrote down was I actually asked to find? The magnitude, right? So I wanted the apparent power, so it's just this part right here. Don't know. Couldn't tell you. Maybe different sources, maybe a slightly different configuration. Not entirely sure. Perhaps I made a mistake then. Perhaps I made a mistake now. Don't know what you're referring to. Gonna move along. All right, so we just figured out this voltage here. VB. So performing Kirchhoff's voltage law around the left-hand loop will allow us to calculate the RMS phasor voltage VA with the positive polarity on the left, like so. So by inspection, we should pretty easily be able to see that VA is simply this 120 angle 0 minus whatever we just got for VB. Everybody okay with that? So we're going to have 120 angle 0 degrees volts RMS minus 77.917 angle negative 0.238 degrees volts RMS. And I get 42.085 angle 0.441 degrees volts RMS means the complex power absorbed by A is 42.085 volts RMS squared, divided by the complex conjugate of SA, which will be 10 minus J8. Which I get to be 138.304, angle 38.660 degrees, volt amperes, or 107.998 plus J 86.398 degrees. Oh, sorry, not degrees. Volt amperes. Coy, which of this stuff is what I'm actually trying to find? Exactly right. What the heck is happening here? So this is P, A, measured in what unit? Watts. Average power is measured in watts. Reactive power is measured in volt amperes reactive. And apparent and complex power are measured in volt amperes. So the last bits that we need then are the complex powers, or excuse me, the power factors at which our sources are supplying power. So for our voltage source, we need to know the current that's flowing into the negative polarity terminal. So let's call that this guy right here, I VS. How would we go about solving for that quantity? Exactly right. So now that we know what VA is, VA over ZA is that current that we need. And we also need to determine the complex power, or the power factor at which the current source is supplying. So I want the current to be flowing into the negative polarity terminal. So let's call this voltage negative plus VCS. How would I go about determining that quantity? Yeah, VB plus VC. Yeah, KVL around the right-hand loop. So VCS will be VC plus VB. Absolutely. Okay. And then from there, the difference of the angles gives us our power factor angle. And then we take the cosine of that and we're good to go. Well, we're running low on time, so I'm trying to hurry up here. All right. So anybody have any questions about this circuit analysis and all that kind of stuff that we've done here to this point? Everything seemed reasonably straightforward. Sonny, you on board? Okay. I mean, if you want me to slow down or work more things, I'm happy to do it. Legitimately.
I mean, I'll rewatch the lecture. I'm kind of slow.
Okay. All right.
Did I say that's the power factor of each source?
That's correct. So I would need the power factor of the voltage source and the power factor of the current source. And so we know the voltage of this guy. We figure out the current by doing Ohm's law for impedance ZA. Take the difference of the angles, cosine of the angle. For this guy, KVL, so VC plus VB gives us the voltage drop. We already know the current. The difference of the angles tells us what our power factor angle is. Cosine of that gets us there. All right. Power factor correction. Crash course because we have 20 minutes. So if I have a generic inductive load with the following power triangle, let's call this S old. The projection of this onto the real axis will be a quantity we'll call P old. And the projection of this onto the imaginary axis will be a quantity we'll call Q old. Right? So let's call this angle here theta old as well. All right. So if this particular load is operating at too low of a power factor, let's just say for the sake of argument, somewhere around 0.6 efficiency. If we wanted to increase the power factor, would we need to make that angle theta larger or smaller? Smaller, okay? So to make that angle smaller, what we're going to have to do is inject some or supply some bars to the system, which we do by placing a capacitor in parallel with our load, right? Because we know from 15 to 20 minutes ago that capacitors supply complex power. All right. So if we were to add some complex power using a capacitor, which I'm going to call S cap, the resultant, I can add these vectors effectively tip to tail. So that putting it there would be the same as doing this. And our resultant would be this guy right here, which I'm going to call S new. And S new has an angle theta new, like so. So our relationships here are as follows. S old is equal to P old plus JQ old, and S new is equal to S old plus S cap. The complex power is being provided by our capacitor. Which can be written as P old, because the amount of average power absorbed by our load does not change. Plus JQ new. Okay. So since S cap is S new minus S old, this is P old plus JQ new minus P old plus JQ old, which is simply J Q new minus Q old. This quantity will always be negative. Okay. Because the whole point is that after our power factor correction capacitance has been applied, the imaginary part, JQ or Q new, is smaller than what it used to be. Okay. So that quantity is always negative. We can call this just simply JQ cap. Since Q cap is equal to negative omega C VRMS squared. Okay. So this is simply just the complex power, or actually take that back. This is the reactive power absorbed by a capacitor, which is the imaginary part of negative J omega C VRMS squared. If we make these two things equal to each other, what we find is that C is equal to negative Q cap divided by omega VRMS squared, which can also be expressed as P old times the tangent theta old minus the tangent theta new, all divided by omega VRMS. So this tells us what size capacitor we need to introduce in parallel to our load in order to correct the power factor from some old power factor angle to some new power factor angle.
If you want a perfect power factor,
So you don't ever want, so power factor of 0 means that you're operating at 100% inefficiency. Yeah, power factor of 1, exactly right.
and I think
Then-
zero.
Then theta new would be 0 degrees, absolutely right. So let's work a quick example here, or try to in the next 13 minutes. All right. So let's say that I have the following circuit. I have some RMS phasor source voltage Vs. And that voltage source Vs is supplying power to two loads by way of a transmission line that has an impedance of 0.05 plus J 0.2 ohms. My first load I'll call load number 1, absorbs 20 kilowatts at a power factor of 0.7 lagging. And my second load absorbs 12 kilovolt amperes at a power factor of 0.9 leading. And let's say that the voltage drop observed at the load is 240 angle 0 degrees volts RMS at 60 hertz. 60 hertz. We want to know what value of C will make the source supply power at PFS is equal to 0.95 lag. So effectively, what I am saying here is we are going to install some capacitor C in parallel with our source. That's usually where we actually apply our power factor correction capacitor bank. It usually doesn't make sense to correct the power factor of individual loads. We want to correct everything downstream from our transformer. Okay. All right, so if we look at our equation here, I'm going to scroll back here. Let's figure out what we need to determine. Do we know P old? No. Do we know theta old? Also no. Do we know theta new? Pretty much. Do we know omega? Yeah, pretty much. Do we know VRMS? I disagree. Right, because VRMS is VS in this case, right? So this represents the voltage drop across the capacitor, which is our source voltage, not the voltage drop over our loads. If we were trying to correct the load, we could use the 240 angle 0 or whatever, but we're not correcting at the load, we're correcting at the source. So we need to know what that source voltage is. So we have our work cut out for us. Yay. All right, so if we want to figure out the quantity P old, we effectively need to look at everything to the right of the capacitor as behaving like a single load, okay? That will be operating with some combined complex power, okay? So to get to that point, let's figure out what the complex power for load 1 is, complex power for load 2, and the complex power of our transmission line, all right? So complex power for load 1. Anybody have any thoughts how we could determine that based on the information that we're presently getting?
Average power.
We have the average power and the power factor.
Power factor.
Okay, so power factor is the cosine of the power factor angle. Okay, so if we know the power factor, we can work backwards to get our power factor angle. All right. Right. So let's say we're going to have an angle of inverse cosine of 0.7, and this lagging here tells us that our angle should be positive. So the inverse cosine function is always going to give us a positive number. So when we're doing this one in a moment, we'll have to remember to put a negative sign in to force the angle to be negative, because a leading power factor always has a negative. All right, so we get the angle bit figured out. Power factor by definition is the ratio of the average power divided by the apparent power. Well, complex power is the apparent power angle, power factor angle. So I would argue that this guy right here should be 20 kilowatts divided by 0.7. So I'm saying, apparent power is average power divided by power factor. So just to let you guys know where these relationships are coming from, power factor is P over the magnitude of S, which is the same as cosine S. So we're actually using both of these representations to fully describe the complex power absorbed by load 1. So if we do the math here, we'll find that we get 28.571 with an angle of 45.573 degrees kilovolt amperes. Complex power absorbed by load 2 is going to be similar. So what does this 12 kVA right here represent? Caleb, got any thoughts? The units tell us what part of the complex power this is, right? So what are the units of average power? Watts. What are the units of reactive power? What are the units of apparent power? This, voltamperes. So this is our apparent power, which by definition is the magnitude of our complex power. So we just take this number, we don't need to divide by the power factor or anything like that. We're actually already given what we were looking for there. So this is going to be 12 kVA with an angle of inverse cosine of 0.9, but since we have a leading power factor, our angle must be negative, which means we need to force that to happen by including a negative sign. This is going to give us 12 angle negative 25.842 degrees kVA. And the total complex power absorbed by our composite load, those two loads in parallel, is simply S load 1 plus S load 2, which is 34.335, angle of 26.227 degrees kilovolt amperes. So we have this bit figured out. We have barely over a minute left of class, so I say we resume this at the beginning of our next lecture.